Hi everyone. In this video we are going to start Unit 4, Organometallics and Umpolung strategy. And using organometallics is one of the best ways to make a carbon-carbon bond. And within the star I put 5 reagents that you could react an organometallic with to get a bunch of different products. This is also used in industry, and I have 4 pharmaceuticals that were made using this organometallic strategy or Umpolung. That means polarity reversal. I'll write about that in just a bit. Tramadol, I think that's a pain reliever. Tamoxifen is being used to treat breast cancer. Ibuprofen is another, maybe fever and pain reliever. And I'm not going to try to pronounce this, but I think this is an antifungal. And the bond that was made, the carbon-carbon bond that was made in each of these pharmaceuticals is represented in pink, and it used this or a very similar strategy to this. Okay, enough about that. I have a couple of definitions to get to you, and the first one is organometallics. Now, a Grignard and an organolithium is a type of organometallic molecule. And an organometallic is exactly what its name suggests. It's an organic part of the molecule and a metallic part. So for instance, well, let me just write that down. It has an organic part. Organic meaning it contains carbon and hydrogen, plus a metal. And we could generalize that by this abbreviation, and M equals metal. The metals we'll be working with in this video are going to be magnesium and lithium and also copper. Okay. But what about this Umpolung? What is that? It says here that we're going to synthesize these reagents to cause an Umpolung, and we're going to see that reaction with, hopefully, epoxides. So an Umpolung is a German word, meaning polarity inversion. Okay. So we are going to use or make these reagents to cause a polarity inversion. And really what that means is it's a modification of a functional group with the aim to reverse a bond polarity. Okay. So let me, oops, my other laptop is about to die. 1 second. Oh my goodness. Okay, let me give you an example. If we have an alkyl halide, we should be able to draw partial positives and partial negative charges on that molecule. And we have a bromine, which is electronegative, pulling electrons away from the carbon. And we've seen that before. We've seen carbon with partial positives because even a carbonyl group, right? A carbonyl group also has the same type of bond dipole, which makes a carbon partial positive. A lot of the reactions that we've seen in the past, the carbon is an electrophile. It wants to be attacked by a nucleophile. Okay. By creating these organometallics, we're going to reverse the polarity and now have carbon as a negative or partial negative. So here's one example. We put a lithium, we replace a bromine with a lithium, and we're able to accomplish, Umpolung or polarity inversion. Now, the thing is, there are two ways to think about this molecule. When you have a metal that is very electropositive, you could also think of it as this. And when you draw the mechanism, I typically use the bond, but you're also allowed, if you draw it in this fashion, you're allowed to use a lone pair. Because what is carbon acting like now? Carbon is the electron rich. Carbon is the nucleophile. Okay. All right, so let's get to our first reaction, which is the synthesis of a Grignard. And actually, we're going to put both the synthesis of a Grignard. Let me double check. Yeah, synthesis of an organometallic. And we have two types, the Grignard and the organolithium. There are other types of organometallics. We'll see one probably later in a couple of videos from now. But the two we're going to be concerned with here are going to be what's called a Grignard reagent and organolithium. Okay. Let me show you the Grignard first. For Grignard, you're going to start with an alkyl halide. It doesn't matter if it's primary, secondary, or tertiary. And you're going to add magnesium metal. And you could indicate magnesium like Mg. It's not an ion. Or you could, I like to put a 0 to emphasize that it's neutral. Or you could write the word metal. The other thing that you might see with the reagent is the solvent. Solvent is important in this case because you don't want any protic solvents around when you make the Grignard or the organolithium. And I'm going to use diethyl ether. And the abbreviation that we can use for diethyl ether is ET2O. And this is a little bit strange. You're going to keep the bromine, but the magnesium is going to insert itself. Okay. It still doesn't change the fact that this carbon is partial negative and this magnesium metal is partial positive. Okay. Now, what's interesting about these organometallics and making them, actually, let me give you organolithium, and then I'll discuss what's very unique about these molecules. So we had a primary alkyl halide. We can also have a tertiary, and again, lithium, neutral. Another solvent that you can use to make the Grignard or the organolithium reagent is THF. That's tetrahydrofuran. And if you forgot what that looks like, it looks like this. It's an ether. This is also an ether. Diethyl ether looks like this. What's important is that there are no acidic hydrogens. In this case, you are going to literally displace the bromine with a lithium, and you could have that. Now, I did mention that there is another way to draw this by drawing out the formal charges. Again, for mechanisms and for fill in the blanks, I like the one that shows the bond, but you could also think of it as this. You could break it up into its ions. And the thing about the Grignard reagent, the main way people draw it is in brackets with a plus. It's a complex. I'm not sure why there's a bracket typically, but that's what I've seen most of the time. And I didn't write this down, but this is called a Grignard for, I think, Victor Grignard, who I believe he must have won the Nobel Prize for this. This is a very unique reaction, an important reaction. Okay, and again, this is the organolithium. Okay, What's unique about this? Look at this alkyl halide. And it's not even an alkyl halide, it's bromobenzene. Okay. By the way, you could use chloro. Um, Typically, bromine and chlorine are the halides that you would use. But you might have heard me say that you cannot substitute on an sp2 carbon. When you did your SN1 and SN2 reactions with alkyl halides, right? You'd never substitute, you never do an SN1 or an SN2 on a carbon that is on the double bond. It always has to be primary, secondary, or tertiary on an alkyl chain. But for the synthesis of organometallics, you can substitute this out. I typically like using the Grignard reagent or making the Grignard reagent, so I'm going to do that here. But you could easily have done lithium. Just don't forget that for the Grignard reagent, you have the Mg and you keep the Br, or the Cl if there was a chlorine. All right, let's do one more example. You fill in the product for this. We'll put a chlorine. I can make it even crowded. It doesn't matter. These go very well. Oh, let me put a solvent actually. Et2O, it's typically the preferred solvent. I'll show you why, or I'll tell you why in just a bit. Go ahead and draw the product for this reaction, please. Okay. I'm not going to draw, you've seen it before, you might see it in your textbook, or your professor might draw it this way. Again, I like the form where you see the covalent bond between the metal and the carbon. Now, when you do this in lab, and there are some schools that do the Grignard reagent, or the synthesis of the Grignard reagent in the lab, you have to use a solvent that has no protons, acidic protons. By the way, I put these two together because whatever you can do with a Grignard, you could do with an organolithium. It's just that I prefer the Grignard a lot, okay? And I think most professors do. And honestly, I've never seen a college lab experiment where they made organolithiums. It's always making the Grignard. Let me show you why it's important that there's no acidic protons. And this is a warning because you will mess up your experiment if you try to make a Grignard reagent in a protic solvent, or if there's any protic solvent after you made the Grignard reagent and you're trying to use it. Because when you have the Grignard reagent, let me draw the first one that we made. And again, this is a warning. And here you cannot have acidic protons. And even water is acidic enough to ruin your Grignard. So it cannot have acidic protons if you want to use, let's say if you want to make or use organometallic. Because that carbon is very partial negative, it could not only act like a nucleophile, it could act like a base. It could grab a proton. So if your solvent or any residual moisture is around, or if your solvent has a acidic proton, that will grab the hydrogen. And let me give you two examples. The first example is the first Grignard that we made. And if you have anything like methanol, okay, methanol is a common solvent, but you can't use methanol when you try to make an organometallic, or in this case a Grignard, because you will grab the proton. So that's our first mechanism arrow. And oh, yikes. That's not a Grignard reagent. I forgot the Mg. Oh man. Okay. That's not good. Don't draw that. My bad. Grignard. Plus any protic molecule. Okay. Now let's draw the mechanism. From the bond connecting the carbon and the metal. Again, this carbon is very partial negative. But I'm not drawing, right? You have to draw from a source of electrons. So you could draw from the bond. Or if you drew out your Grignard reagent like this, you could use the lone pair. Okay. Always start your mechanism arrow from a bond or a lone pair or a radical, an unpaired electron. And we have this. And how do we want to draw this? Oh, okay, this is how we're going to draw it. See, that bond is broken, and this had 2 hydrogens, and now it has 3. We totally destroyed this Grignard reagent. Plus what? We have OCH3 minus, and we have the salt because that MgBr piece is actually positive. That's a mechanism where you could say that, oh, you maybe accidentally destroyed the Grignard. Now the thing is, after you use the Grignard, let's say we use the Grignard properly, and I haven't shown you in reaction just yet using the Grignard, but after you've used it, then you can have acid around because it's used already. It's done its job. Okay, even this one. Okay, do you know the product if we use this Grignard reagent with a benzene ring? Okay. Let's use water. Let's say that it's a very humid day and you made the Grignard reagent and you're storing it and you want to use it in the lab, but it's either the AC is out or it's very humid inside. You have enough residual water in the air to do what? To do this. Okay, can you draw me the product here? All you have to do is draw benzene. I wouldn't do this normally, but see there's an H right there. That wasn't there before. And since we're drawing a mechanism, yeah, let's draw the rest of the products. MgBr. Now, if it was a lithium, you would just have OH and Li, making a salt, most likely, lithium hydroxide. Okay. Anything you could do with a Grignard, you could do with an organolithium. Again, but in this case, we destroyed with residual water. You gotta keep, therefore, solvents need to be dry. Another word for dry, especially in the sense of solvents, is anhydrous. No water dissolved, which is not easy. You leave an ether can open to air. That ether is going to absorb moisture, absorb water, and then you have to dry your ether before you actually use it. And there are some undergraduate laboratory experiments that ask you to dry your solvents before using them. Okay, and the 2 solvents we're going to focus on really are going to be diethyl ether and THF. Now, what can we do with these organometallics, these Grignards and these organolithiums? We are going to react them with epoxides. This is reaction B. We can't forget what epoxides are and how they react. And we can't forget how they open up. Do you remember ring opening of an epoxide? We're going to do the same thing with these reagents. So we're going to call this organometallics. plus epoxides. And we're going to, right away, we're going to start with an epoxide that has stereochemistry. Now, in the previous unit, maybe not previous unit, but in unit, I think 1, when we talked about alcohols, ethers, and epoxides, you learned that there are different ways that you could open up the epoxide. The classic epoxide to use is typically one with a ring and one that is not symmetrical. Okay, because we're going to be concerned about the regio selectivity and the stereo selectivity. Let me give you a simple Grignard reagent. Let's say we have CH3, CH2, MgBr. I'll start mixing it up. I probably want to give you more examples with lithium as well. Number 2, acid. Okay. You might ask or say, we gotta wait, we gotta pause, because I thought you said that we can't have any acidic protons when we do a Grignard reaction or when we use a Grignard. The thing is, you know what 1 and 2 means. 1 and 2 means that you react the starting material with the first reagent, purify the intermediate, and then do the second reaction. The thing is, by the time acid comes into play, the Grignard had done its job. The Grignard had what? The Grignard had attacked. Because again, your organometallics are going to act like nucleophiles. Okay, typically they act as nucleophiles. When they acted like a base here, that was unintentional. Normally you don't want to do this. I can't think of a reason why you would want to do this, unless you want a fancy way to get back to the hydrocarbon. Okay? But forget about that. Let us remember what happens with epoxidation, or the ring opening of epoxides. Not epoxidation, but the ring opening of epoxides. When you're not in the presence of acid, when the nucleophile attacks, you will attack the less substituted carbon. It's this carbon right here. Why do I consider this not in the presence of acid? Because the attack happens before the acid step is used. Okay? You are adding an ethyl group, and do you remember how it attacks? It attacks from the backside. So what is the backside of this dash? Again, your attack is going to happen there, and your ring is going to open. The backside of a dash is wedge. So this is what your Grignard reagent's doing. It added the alkyl group. Okay. And then we open up the ring. That dash for the oxygen is still there. That methyl is still wedged. Okay. And now that proton source adds this hydrogen to the O-. Should we do the mechanism? Let's show you the mechanism real quick. And yep, I should have time to do another example. You will never add, I'll tell you this, you will never add an organometallic in the presence of acid, because you will destroy your organometallic if you have any acid in the same reaction. So that's a good tip, because we'll never be under acidic conditions when the organometallic reacts. We'll never attack the more substituted carbon. Now, how would I draw this? Again, I like to draw the organometallic with the covalent bond, not with the ions, but not a big deal. Your bond, you're going to start with your bond, and you're going to attack that carbon. Okay, try to do a better job than me, because I should have realized or remembered that I am going to have to break this bond, the dash, and put it onto oxygen. Okay. For my class, when they draw mechanisms, I typically am not worried about the stereochemistry, but here I am going to worry about the stereochemistry to kind of demonstrate why this happens. Why is that alpha group wedge? So we came from the front because front is the quote unquote backside of the dash, and we did add two carbons, and I'll draw it like that. Yes, I know we have an MGBR somewhere. So I'm just going to draw it off to the side. But maybe there was a better place to draw this because when we made the O minus, oh, that's good. We could have had a salt. Okay, maybe I should draw this a little bit closer. And the methyl group stays the same. And then finally, not finally, but next is you have the protonation. And the protonation of the alkoxide. What did we make? It seems like we made in this case, a tertiary alcohol. A tertiary alcohol. When we reacted an epoxide with a Grignard reagent. Why is it tertiary? Because, this carbon here that would ultimately have the OH is tertiary. It has 3 other carbons around it. But if we use another type of epoxide, maybe we won't get a tertiary alcohol. Let me give you one more example, and now I'll use the lithium, organolithium. And let us use a pretty simple epoxide. Now, another thing that you want to not get freaked out about is, what am I saying with this formatting? I'm saying that in one reaction flask, I'm going to mix these two together. Get the product, purified, and then in the second reaction, I'm going to add acid. But I could have switched these places. I could have had the organometallic as the starting material and the epoxide as the reagent. It doesn't matter. Both of these are going into the pool. You understand what I'm saying? Because I could have done this. I could have given us this organolithium as the starting material, and then as reaction 1, given this epoxide. It's the same thing as putting the epoxide here and the organometallic on reaction 1. Number 2 is always going to be acid. So think about what happens here. Now, I may not have time to draw the mechanism, but I could show you a pseudo mechanism. I could pretend that this comes here to the left substituted carbon, and then I open up the ring. The product here would look like this. Okay, the ring opened up. Now, just be very careful because I can switch up the type of R group on the metal. We're adding actually 2 carbons, and they're connected to each other with a double bond. This bond existed, so I like to put a dot just to keep track of the carbon that I'm attacking. And I attack that dot with this now alkene, right? Because you're making the attachment between the dot and the carbon right here. Oh man, sorry about that. Yikes. This is about to lose charge. There we go. My bad. All right. And then finally, we put the hydroxyl group, protonate it. Okay. Okay. So that is reaction A to make the organometallic. We had a warning about not using any acidic protons or having any acidic protons available. Okay, so that's a warning. And then we did reaction B using organometallics with epoxides. You notice that this carbon is not chiral, so I don't put wedges or dashes. This carbon is not chiral also, no wedges and dashes. Okay? Practice, understand what carbons you're attaching or bonding. You're bonding the dot with the carbon that was attached to the metal. Oh my. Got all twisted. Sorry about this. Okay, there's your example. And there's your example.